What is nanochemistry? Nanochemistry is the branch of chemistry that deals with the study, creation, and manipulation of materials at the nanometer scale, where 1 nanometer is 1 billionth of a meter. At this incredibly small scale, chemical properties can be drastically different from those at larger scales, leading to unique and useful behaviors in materials. Why is nanochemistry important? New materials with special properties. Nanochemistry allows us to create materials with specific properties that are not possible with bulk materials. For example, nanoparticles can have enhanced catalytic properties, making chemical reactions faster and more efficient. Medical applications. In medicine, nanochemistry enables the development of targeted drug delivery systems. These can deliver drugs directly to disease cells without affecting healthy cells, much like a highly precise missile that hits only its intended target, reducing side effects and increasing treatment effectiveness. Environmental solutions. Nanochemistry can be used to create materials that can clean up pollutants or convert waste into useful products. Think of it as a tiny, powerful vacuum cleaner that can clean up toxins from water or air with high efficiency. Analogies to understand nanochemistry. 1. Lego blocks versus nanochemistry. Imagine building structures with Lego blocks. Regular chemistry is like using large Lego blocks to build things, which has limitations in detail and precision. Nanochemistry is like using incredibly tiny Lego blocks that allow for much more detailed and precise structures. This precision enables the creation of materials with very specific properties. 2. Cooking with ingredients versus nanochemistry. In cooking, you mix ingredients to create a dish. In regular chemistry, these ingredients are relatively large molecules. In nanochemistry, you are using the tiniest possible ingredients, atoms and molecules, to create new dishes, materials, with unique flavors, properties, that cannot be achieved with larger ingredients. Examples of nanochemistry applications: drug delivery systems. Nanochemistry enables the creation of nanoparticles that can carry drugs to specific parts of the body. For example, in cancer treatment, these nanoparticles can target tumor cells directly, releasing the drug where it's needed most and minimizing side effects. This is akin to having a GPS-guided delivery truck that only drops off packages at the exact correct address. Solar cells. Nanochemically engineered materials can significantly improve the efficiency of solar cells. By using nanoparticles, we can create solar panels that capture more sunlight and convert it into electricity more efficiently. It's like upgrading from a regular solar panel to a super efficient one that produces much more energy from the same amount of sunlight. Catalysts for industrial processes. Nanoparticles can serve as highly effective catalysts in industrial chemical reactions, speeding up processes and making them more efficient. For instance, in the production of fuels or chemicals, these catalysts can reduce the energy required and increase yield, similar to how a highly skilled chef can prepare a gourmet meal faster and with better results than an amateur cook. Why is nanochemistry special? Enhanced surface area. At the nanoscale, materials have a much larger surface area relative to their volume compared to bulk materials. This increased surface area can lead to greater reactivity and efficiency in various chemical processes. Quantum effects. Nanochemistry takes advantage of quantum effects, where the properties of materials change significantly at the nanoscale. These effects can be harnessed to create materials with unique electrical, optical, and magnetic properties that are not seen in larger scale materials. Precision and control. Nanochemistry allows for the precise control of the composition and structure of materials at the atomic and molecular levels. This precision enables the design of materials with tailored properties for specific applications, leading to innovations across many fields, including medicine, energy, and electronics. Nanochemistry is a revolutionary field that focuses on the manipulation of materials at the atomic and molecular levels to create new materials with unique and enhanced properties. Its significance lies in its ability to drive advancements in technology, medicine, environmental science, and industry by leveraging the unique behaviors of materials at the nanoscale. The world of nanochemistry is about harnessing unique properties to create a future brimming with possibilities. Imagine diseases diagnosed and treated at the cellular level and energy flowing freely from sustainable sources. Materials designed with atomic precision to exhibit desired properties. The power of nanochemistry lies in the unique properties of materials at the nanoscale. Remarkable tools allow us to explore and manipulate this hidden universe. The scanning tunneling microscope, or STM, earned its inventors the Nobel Prize in Physics in 1986. The STM allows us to see and manipulate individual atoms. The transmission electron microscope, or TEM, magnifies objects over 1,000,000 times. Nanochemists are pushing the boundaries of our understanding, unlocking the nanocosmos' potential. The seeds of nanochemistry sprouted from human curiosity, a desire to understand the world at its most fundamental level. Visionary physicist Richard Feynman, in his 1959 lecture, proposed writing the Encyclopedia Britannica on the head of a pin. Feynman envisioned controlling matter atom by atom. Early pioneers drew inspiration from nature's nanoscale engineering. From butterfly wings to gecko hairs, nature showcased the power of nanoscale structures. The 1980s marked a turning point in nanochemistry with groundbreaking discoveries and inventions. In 1981, Gerd Binnig and Heinrich Rohrer invented the scanning tunneling microscope. This revolutionary tool earned them the Nobel Prize in Physics in 1986. In 1985, the discovery of Buckminster fullerene, or buckyball, was another milestone. These discoveries, along with the atomic force microscope, advanced nanochemistry. With powerful nanoscale tools, nanochemistry blossomed. Scientists synthesized tailored nanomaterials, unlocking technological innovation. Nanoparticles emerged as versatile nanomaterials. Researchers explored nanotubes and nanowires. This led to nanomedicine and nanoelectronics, promising solutions to global challenges. Welcome back to our exploration of nanochemistry. We've journeyed through historical milestones and pioneering discoveries. Now let's delve into the fundamental principles of nanoscale behavior. Nano denotes 1/1,000,000th of a meter. Imagine shrinking to the size of an ant. A grain of sand would appear as large as a mountain. Enter a realm where particles exist in multiple states. The strange world of the ultra-small. In the nano world, we encounter quantum mechanics. Wave-particle duality. Particles can be waves. Quantum tunneling. Particles pass through barriers. Section 3. Surface area is king why size matters at the nanoscale. Nanomaterials have a high surface area to volume ratio. This increases their reactivity and properties. More atoms are exposed, making them ideal for catalysis. Section 4. From nanometers to new materials. A world of possibilities. The unique properties of nanomaterials arise from size-dependent effects, quantum phenomena, and enhanced surface area. This has opened up a world of possibilities for designing materials with tailored properties. From quantum dots in displays to carbon nanotubes in composites, nanomaterials are revolutionizing various fields. In medicine, nanoparticles enable targeted drug delivery, minimizing damage to healthy tissues. In energy, nanostructured materials enhance solar cells, batteries, and fuel cells. Researchers are exploring their potential in water purification, environmental remediation, and computing. The nano world reveals wonders, challenging our understanding of matter and its possibilities. Welcome back to our exploration of nanochemistry. We're now ready to embark on a captivating safari through the diverse and awe-inspiring world of nanomaterials. The nano world presents a dazzling array of materials, each possessing remarkable properties from their minuscule dimensions. Imagine materials as thin as a single atom, carbon nanotubes stronger than steel, and particles 1,000 times smaller than a human hair displaying dazzling optical effects. This is the captivating realm of nanomaterials, pushing the boundaries of material science. Fasten your seatbelts as we embark on this exhilarating journey through the diverse zoo of nanomaterials. Our first stop on this nanoscale safari brings us to the captivating world of nanoparticles, the tiny titans of nanomaterials. These minuscule particles, ranging from 1 to 100 nanometers, exhibit remarkable properties that differ dramatically from their bulk counterparts. Shrink a gold nugget to a few nanometers, and it transforms, shimmering with vibrant shades of red, purple, or blue. This color change arises from surface plasmon resonance, where electrons oscillate in response to light. Their small size and high surface area also endow them with exceptional catalytic activity. For example, platinum nanoparticles are used in catalytic converters to scrub harmful pollutants from automobile exhaust. Their unique properties make them ideal for biomedical applications, including targeted drug delivery, imaging, and diagnostics. As we venture into the nano world, we encounter materials with dimensions confined in one or two directions, giving rise to unique properties. These include nanotubes, nanowires, nanorods, and nanofilms, with potential applications in electronics and energy storage. Imagine graphene, a single atom-thin material stronger than steel and more conductive than copper. Discovered in 2004, graphene earned the Nobel Prize in Physics in 2010, sparking extensive research. Its strength comes from strong covalent bonds, and its conductivity from its unique electronic structure. These properties make graphene ideal for next-generation electronics and energy storage. Carbon nanotubes, rolled-up graphene sheets, exhibit exceptional mechanical strength and electrical conductivity. They are used in high-strength composites, flexible electronics, and nanoscale sensors. Nanowires, ultra-thin wires, exhibit unique electrical and optical properties due to quantum confinement. Nanofilms, ultra-thin layers, play crucial roles in various technological applications. Anti-reflective coatings on eyeglasses and solar cells rely on nanofilms to enhance light transmission. Section 4. The allure of carbon fullerenes and graphene. Carbon forms the backbone of life and exhibits a remarkable talent for self-assembling into fascinating nanoscale structures, including fullerenes and graphene. Fullerenes, discovered in 1985, are cage-like molecules composed of carbon atoms arranged in pentagons and hexagons. The most famous fullerene, C60, consists of 60 carbon atoms arranged in a perfect sphere, known as buckyball. Graphene, a single layer of carbon atoms in a honeycomb lattice, possesses extraordinary strength and high electrical conductivity. Its flexibility and transparency make graphene a promising candidate for applications like flexible electronics and high-speed transistors. The discovery of fullerenes and graphene has opened a new chapter in carbon chemistry, revealing the element's potential for revolutionary nanomaterials. Welcome back, fellow explorers. Let's dive into the ingenious methods scientists use to create nanomaterials. Nanofabrication is like assembling intricate Lego models with atomic precision. There are two primary approaches: top-down and bottom-up. Top-down is like chiseling a statue from marble. Techniques like lithography etch patterns onto materials. Bottom-up is like building a statue atom by atom. Techniques include chemical vapor deposition and self-assembly. Each method has its pros and cons, depending on the material and application. Our first stop in nanofabrication is chemical vapor deposition, or CVD, a versatile technique for depositing thin films onto substrates. Imagine a painter spraying a fine mist of paint onto a canvas, building up layers of color. CVD uses gaseous precursors that react on a heated surface to deposit a thin film. Inside a CVD chamber, a controlled mixture of gases is heated to a specific temperature. These gases decompose on a substrate, depositing a thin film, atom by atom. The beauty of CVD lies in its versatility and control. By adjusting gases, temperature, and pressure, scientists can tune the film's properties. This control makes CVD essential for creating nanomaterials for microelectronics and coatings. Section 3. Sol Gel. Processing crafting nanomaterials from liquid solutions. Our next stop on our nanofabrication tour brings us to the fascinating world of sol gel processing, a versatile technique for creating nanomaterials from liquid solutions. Sol gel processing involves transforming liquid precursors into solid materials through controlled chemical reactions. The process begins with a sol, a colloidal suspension of tiny particles dispersed in a liquid. As the sol ages, particles link to form a gel, a jelly-like substance. The gel is dried, leaving a solid material with a porous network of nanoparticles. Sol gel processing is ideal for creating ceramic and glass materials with tailored properties. For example, silica aerogels, known for their insulating properties, are made using this method. These aerogels, often called frozen smoke, have the lowest thermal conductivity, perfect for insulation and aerospace. Section 4. Self-assembly. Nature's blueprint for nanoscale construction. Self-assembly in nanotechnology harnesses nature's principles, where atoms and molecules spontaneously arrange into ordered structures. Imagine birds forming a V shape or fish swirling in unison, creating patterns from simple rules. This bottom-up approach allows building blocks to assemble into desired structures with minimal intervention. DNA formation is a prime example, where strands intertwine guided by base pairing. Self-assembly has applications in electronics, photonics, medicine, and materials science. Section 1. Unveiling the Nano World. Tools for seeing the unseen. Welcome back to our nanochemistry adventure. Now, we turn our attention to characterization, an equally crucial aspect of nanotechnology. Imagine discovering a new species of insect, its intricate wings shimmering with iridescent colors. Before understanding its behavior, we need to observe and measure its features. Similarly, characterization techniques help us see and understand nanomaterials. These techniques provide invaluable information about size, shape, composition, and properties. Techniques are broadly classified into microscopy and spectroscopy. Microscopy visualizes nanomaterials revealing size, shape, and surface features. Spectroscopy reveals chemical composition, electronic structure, and bonding characteristics. Prepare to be amazed by the ingenuity of these tools and the wealth of information they provide. Section 2. Microscopes as our eyes, zooming in on the nanoscale. Microscopy is a cornerstone of nanotechnology, allowing us to see atoms and molecules. Microscopes provide breathtaking glimpses into the nanoscale, unveiling hidden architectures. Two key microscopes in nanotechnology are the scanning electron microscope, SEM, and the transmission electron microscope, TEM. SEM uses a focused beam of electrons to scan a sample's surface, revealing its features. TEM, like an X-ray, allows us to see the internal structure of nanomaterials. In TEM, electrons pass through an ultra-thin sample to create an image. SEM and TEM reveal nanomaterial morphology and internal structure. Section 3. Deciphering the language of atoms. Spectroscopy in nanochemistry. Imagine listening to an orchestra playing a symphony. Each instrument produces a unique sound, characterized by its pitch, timbre, and volume. Spectroscopy in nanochemistry operates similarly, using light to listen to the vibrations and electronic transitions of atoms and molecules. Each element and chemical bond absorbs and emits light at specific wavelengths, creating a unique spectral fingerprint. X-ray diffraction, or XRD, uses X-rays to determine the structure of a crystal lattice. Analyzing the diffracted X-rays reveals the arrangement of atoms within the crystal. FTIR measures the absorption of infrared light to probe molecular vibrations. Each chemical bond vibrates at a specific frequency, revealing functional groups in a molecule. Raman spectroscopy uses inelastic scattering of light to study vibrational modes. Analyzing frequency shifts provides complementary information to FTIR. NMR exploits the magnetic properties of atomic nuclei to study structure and dynamics. Combining these techniques reveals a nanomaterial's identity and characteristics for various applications. We've journeyed deep into the nano world, exploring its history, principles, and the diverse cast of nanomaterials. Now let's unravel the true magic of nanochemistry, the extraordinary properties that emerge at the nanoscale. Imagine materials changing color with size, sheets stronger than steel, and particles capturing sunlight efficiently. This is the realm where classical physics blends with quantum mechanics, creating fascinating phenomena. At the heart of this transformation is the increase in surface area to volume ratio. Imagine a loaf of bread. As we slice it thinner, the crust to interior ratio increases. Similarly, as nanomaterials shrink, the proportion of surface atoms increases. This abundance of surface atoms enhances reactivity and properties of nanomaterials. Surface atoms interact readily, making nanomaterials ideal for catalysis. Confinement of electrons leads to quantum confinement effects, altering properties. Electrons confined in tiny spaces lead to quantized energy levels, like musical notes. This alters optical properties, causing size-dependent color changes and enhanced light absorption in solar cells. Section 2. Nanomaterials in action, revolutionizing technology and industry. The extraordinary properties of nanomaterials are transforming industries from electronics and energy to medicine and manufacturing. Imagine flexible smartphones, cellular-level disease diagnosis, and lightweight yet strong construction materials. In electronics, nanomaterials push the boundaries of miniaturization and energy efficiency. Graphene enables smaller, faster, and more efficient transistors. The energy sector is also shifting thanks to nanomaterials. Quantum dots in solar cells enhance energy conversion efficiency. Nanostructured electrodes boost battery capacity and charging speed. Nanocomposites with carbon nanotubes or graphene are stronger and more durable. Section 3. Healing, Powering, and Cleaning. Nanochemistry for a better world. Nanomaterials offer promise for addressing disease, energy scarcity, and environmental pollution. In medicine, nanomaterials revolutionize drug delivery and diagnostics. Tiny nanoparticles deliver medications precisely to diseased cells. This approach minimizes side effects and maximizes efficacy. Nanomaterials enable rapid and sensitive diagnostic tools. Nanochemistry enhances solar cells and energy storage. Nanomaterials are powerful allies against environmental pollution. Nanofilters provide clean drinking water efficiently. Section 4. The future is nano-challenges and opportunities on the horizon. At the cusp of the nanotechnology revolution, we face exciting opportunities and critical challenges. Manipulating matter at the atomic level raises ethical, environmental, and societal considerations. A primary concern is the potential toxicity of nanomaterials. Their small size means they can penetrate cells and tissues, impacting health and the environment. Rigorous research is crucial to understand long-term effects and develop safe protocols. Despite challenges, the future of nanochemistry is promising. As our understanding deepens, we anticipate groundbreaking discoveries and innovations. Welcome back, fellow explorers. Let's delve into the nano world, where fascinating phenomena push technological innovation. Quantum dots, tiny semiconductor nanoparticles, exhibit extraordinary properties due to quantum confinement effects. Imagine shrinking a grain of sand to a size 1,000 times smaller than a human hair. At this scale, quantum mechanics takes center stage, revealing strange behaviors. Quantum dots, made of materials like cadmium selenide, are prime examples. Their size-tunable optical properties are captivating. By adjusting their size, we can tune the color of light they emit. This has revolutionized display technologies, leading to QLED displays. Imagine watching a nature documentary on a QLED TV with vibrant, realistic colors. Nanomaterials are revolutionizing catalysis, accelerating chemical reactions with profound industrial implications. Imagine a factory where workers efficiently assemble products. Catalysts speed up reactions without being consumed. They provide alternative pathways with lower activation energies. Nanomaterials with high surface area and unique properties make exceptional catalysts. In catalytic converters, platinum nanoparticles convert toxic pollutants into less harmful substances. Nanocatalysis is crucial for clean and sustainable energy technologies. Our final stop on this journey through advanced topics in nanochemistry brings us to the fascinating world of self-assembled monolayers, SAMs, where molecules spontaneously organize themselves into single layers on surfaces. Imagine scattering puzzle pieces on a table and watching in amazement as they magically assemble themselves into a complete picture. Self-assembly in chemistry harnesses this same elegant principle, exploiting the inherent tendency of certain molecules to organize into ordered structures. SAMs are typically formed by molecules containing a head group that binds strongly to the substrate and a tail group that interacts with neighboring molecules. One of the most promising applications of SAMs is in biosensing, creating highly sensitive surfaces for detecting biomolecules. SAMs are also finding applications in areas such as corrosion protection, microfluidics, and molecular electronics. In microfluidics, SAMs create patterned surfaces that control liquid flow, enabling lab-on-a-chip devices for diagnostics. The double-edged sword navigating the potential risks of nanomaterials. Nanochemistry presents both unprecedented opportunities and potential risks. Like fire, it offers benefits but also poses risks. Responsible manipulation is crucial to outweigh drawbacks. A primary concern is their potential toxicity. Their small size allows them to penetrate cells, raising health and environmental concerns. Research in nanotoxicology is crucial to assess risks and develop safe protocols. The environmental impact of nanomaterials is another concern. Understanding their behavior in the environment is essential. Careful investigation ensures sustainable nanotechnology development. Shaping a responsible future ethical and societal implications of nanotechnology. Nanotechnology raises ethical and societal implications that warrant careful consideration. Establishing ethical guidelines and regulations is essential for responsible development. Key ethical considerations include the potential to exacerbate social inequalities. Will the benefits be evenly distributed or favor the wealthy? Another concern is the use of nanotechnology for military purposes. Nanomaterials could revolutionize medicine or create lethal weapons. International cooperation is crucial to prevent a nanotechnology arms race. Miniaturization of nanotechnology raises privacy concerns. Imagine nanosensors in everyday objects, collecting data about us. Balancing benefits with privacy protection requires careful regulation. Charting the next frontiers in nanochemistry. The future of nanochemistry is bright, promising to revolutionize countless aspects of our world. Researchers are exploring two-dimensional materials like phosphorine and MXenes. Imagine flexible electronics and ultra-sensitive sensors opening new possibilities. Nanorobots could patrol our bloodstream, and self-healing materials could extend infrastructure lifespan. Embracing the challenges and shaping the future. The journey into the nano world is a collective human adventure. We must ensure nanotechnology benefits all of humanity and safeguards our planet. This requires scientists, engineers, policymakers, and the public working together. Open dialogue and responsible innovation are crucial. The future of nanochemistry is a shared narrative, written by our choices today. Section 1. The Nano Perspective, a universe within reach. Our journey through the nano world reveals nature's elegance and complexity at its most fundamental level. From Feynman's visions to modern labs, scientists push boundaries, creating materials with magical properties. At the nanoscale, classical physics blends with quantum mechanics, giving rise to extraordinary phenomena. We've marveled at nanomaterials like vibrant quantum dots and strong carbon nanotubes. These tools revolutionize industries, paving the way for a future filled with technological marvels. By shrinking to the nanoscale, we reveal hidden connections and possibilities beyond imagination. Section 2. A future shaped by the very small. The nano world, once a realm of speculation and science fiction, is rapidly becoming our reality. Nanomaterials are already in our clothes, cars, medicines, and technologies. Nanochemistry promises to address some of the world's most pressing challenges. Imagine diagnosing diseases at the cellular level and harnessing sustainable energy. The journey ahead is not without its challenges. We must ensure the safe handling and disposal of nanomaterials. By embracing collaboration and ethical considerations, we can harness nanotechnology for a brighter future.